All right, well, good to see everyone. Plan for today is to continue working with functions. So last time we were working with surjectivity, injectivity, bijectivity, those ideas. So today I want to kind of see why being surjective and injective is a really nice property for a function to have. And I guess before we get started, just a couple of things. Yeah, you should be able to see how you did on the multiple choice part, both your score and where you might have lost points on that. So let me know if you have any questions about that. I've been grading the written stuff. I'm hoping to get through that by the end of the week. So I'll have those grades updated once they're done. If anybody is like concerned about grades, I just want you to know that the deadline for withdrawing or changing your grade to a P plus, going through that policy, expired as far as doing it on your own. You can still withdraw or change to the P plus PF policy. At this point, you just need to fill out a form and get approval from an instructor. So if anybody is interested in doing that or discussing that, just let me know. I'm happy to do any of those. But we'll see. We'll give the exams back. So far, their exams are looking fine. Yeah, and otherwise, it's hard to believe we've got 4 classes left. This end of the semester just sneaks up on us with a Thanksgiving break, like right before finals. So the FCQs are open. So for those that are new, FCQs are like course evaluations that are done online. So if you have some time to fill that out, that would be awesome. I'll put an announcement in Canvas for those. But your feedback is really important, both to our department. That's how we make hiring, firing, not really, promotion decisions. So all of these things are factored in. But more importantly, the feedback is helpful for me just to see what works and what I can improve on for other students. So any questions before we get started for today? As far as like work for the rest of the semester, we've got a reading quiz for Wednesday that will be open after class. And your homework assignment, I set the due date to the very last day, or the last day of our class. So the Wednesday after Thanksgiving break at midnight. So it's not due on Monday, it'll be due on Wednesday, and it will be on material in chapters 12 and 14 that we cover. So the plan for today is to finish chapter 12, which deals with functions. So what you guys watched or read about was this notion of composition of functions, probably something you're familiar with. And so we just say we're going to compose G with F, and this is defined as saying you first take A, plug it into F, the inside function. You get some output of F. That output of F you then plug into G. So that's how composition would work. So I want to kind of combine this idea of composition and injectivity, surjectivity, bijectivity together. So if we have this function F, and it's really important here to kind of pay attention to what the domain is, what the codomain is, and what the range might be in order, if we're going to consider these properties. So it's going from real numbers into real numbers given by x squared, and G also mapping from reals into reals is given by sine x. And so the first thing that you want to make sure is if we're going to compose it in this order, then you want to make sure that the domains and the codomains are all matching up. So for example, this would say we first go into F, and what comes out of F is a real number, and then you just want to make sure that the input of the next function can take in the output of the previous function, which is not a problem here because everything is real numbers. And so this is just another way we often just write it like this. This is actually a little bit more clear to see how these functions work. And so in this case, we would take f of x, which is x squared, and plug that into G. Okay, any questions? And so then we want to think about various properties here. So for injectivity, right, we want to check to make sure that every input goes to a distinct output. So there's not two inputs that go to the same output. So what do you guys think about this one? Would this function be injective?
No.
Why not?
Because it's a sine function, and because it's a sine function.
Okay, so for it to not be injective, then we should be able to find two different inputs that get sent to the same output.
Correct.
So what would be two x values that would have the same output from this function?
0 and 2 pi.
So if x is 0, I think you want to be a little bit careful because it's going to get squared when we put it in here.
I was gonna just do 1 and -1.
Yeah, so that would work. I think if you want to go along that lines, you would just want to say like 0 and the square root of 2 pi or something like that would work as well. Yeah, so there are all sorts of different combinations that we could pick here. That's right. Something like x equals -1 and x equals 1. Both have the same output, namely sine of 1. So this function is not going to be injective. And for surjectivity, one way to think about this would be to consider the range of the function and if so, then it's surjective. If not, then it wouldn't be. So I guess I skipped this part of the problem, which was determine the domain, codomain, excuse me, and range for this function. So the domain would be the set of all real numbers, since that would be the first thing that goes into F. And the codomain would be the thing that comes out of G in this case, if we're composing them in this order. Oh, sorry, that's codomain. And what would the range of this function be? So what output values would come out of G of f of x, which we could write as sine of x squared?
Would it be 0 to 1? Or I mean 1 to -1?
That's right. Yep, exactly. So it's the sign, right? So this x squared really isn't going to affect things too much. It's just going to, what comes out of sine are all things between, including -1 up to and including 1. So the range here would be -1 to 1. And since the range and the codomain are not equal to each other, this would not be surjective. Okay, so for example, -4 is not in the range, so this would not be surjective, right? For it to be surjective, we need to map to every single one. Any questions so far? Okay, and so then let's do this the other way. We can do this very similarly. So now if we take f of g of x, then that means we're plugging g into f. And the function g was sine of x. So we would get sine of x squared. Okay, and so the domain, now we would start with what goes into G, since we would start with that. And the codomain would now be whatever that output set of F is, which in this case is R as well. And as far as these other properties, do you think this function is injective? What do you guys think? Can you think of two different x values that would get mapped to the same output value in this map?
0 and 1. 0 and pi over 2.
0 and
Or which ones are the ones that is it pi over 2 and I don't know, whichever one's equal 1 and -1.
So what is sine of 0?
Sine of 0 is 0, isn't it?
0. Yep. Where else is the sign going to be 0?
1, right?
So sine function looks like this. Here's 1. Here's -1. So where are these other zeros going to be located?
Pi.
Pi would be one of them. That's right.
Pi and
2 pi, 3 pi, 4 pi, 5 pi.
oh,
Yeah.
I'm an
All of
idiot.
those.
Yeah.
No, you're not an idiot at all.
I'm
Don't
just
say
not
that.
refreshed.
Yes, so there are lots of different values of x that would get mapped to the same output value here. So it's definitely not injective. So the trig functions have all sorts of problems with this one-to-one. And in addition, we can think about surjectivity here. And to do that, we can consider the range. What would the range of this function be? So what kind of stuff comes out of the sign, right? Not all that different than what comes out here. The fact that we square it means that the range, right, no longer is going to have any of these negative values. It has to be strictly positive. So it's different when we compose the function in different ways is important to point out. They do different operations when we change the order around in general. And so since this range is not equal to the codomain, then this is not going to be surjective. And certainly when you're trying to answer questions like this, we didn't do it, but you could go ahead and if it's easy enough to graph these functions, and you can answer a lot of these questions just by looking at the graph, and that's totally fine too. Okay, any questions? I think I'd like to have you guys just play around with these like we just did. So the idea is to consider two different functions. What happens when I compose G with F? What happens when I compose F with G? And then for those two different functions, so in each example, you're going to have two different functions to consider. Identify domain, codomain, range, and then think about whether it's injective or surjective. Any questions about that? Okay, let's see. Okay, the rooms are open, so please help each other out, and Nat and I will check in to see how you're doing. Okay, so let's back up to this one over here. So in part B, we're looking at f is x cubed and g is e to the x. So in this case, the function g of f of x, excuse me, would just be what we get when we plug f of x into g. And so that would give us e to the x cubed. And so the groups that I checked in with, so if we look at this function, right, the domain, we start with the domain of the inside function. Codomain would be the codomain of the outside function. And then as far as this function being injective, groups said, or at least the groups that I was able to check in with, both said yes on this one. And as far as, do we need to prove it formally? That's not what I was trying to get at here. Certainly we have done this, so it's not bad to practice, but this was more of an informal sort of identification thing. But what's important to note here is if you have f of x, that's x cubed, and then we have g of x is e to the x. Both of those functions are injective. They both pass the horizontal line test, right? So when you compose two injective functions, what you get is something that's injective. So that goes for the bottom one as well. So whatever order we compose them in, if they're both injective, the result is going to be an injective function. And so as far as this thing being surjective, if I compose the functions in this way and I wind up with e to the x cubed, what's the range of that function?
0 to infinity, but it doesn't include 0.
That's right. Thank you. That would be 0 to infinity, and that just comes from the range of this thing over here. So because e to the x doesn't hit everything like x cubed does, then right, it is not surjective. So this is a no. For the same reason, this is going to be a no down here. And just to kind of write these out, g of x was e to the x here. So this function would be e to the x cubed, which is different. If you use your properties of exponents, you actually get something different here. So just be aware of that. But it's going to have the same domain, same codomain, and the same range. Any questions? Okay. And so if you're trying to like prove that this was not surjective, it's easier to prove these things don't have these properties than it is to show that they do, because they need to satisfy properties for all values. So to show that it's not surjective, we could just say set f of g right? That has no solution, so there's no x value that would go into the function f of g of x that would give me an output of 7. So 7 is in the codomain, 7 is not in the range, not surjective. Any questions? Okay, and so then let's take a look at this next one. And so sorry about this. So this was all one problem here. So we've got these sets. X is defined up here. Y is so X is the set of all natural numbers from 1 to 100. Y would be the set of all even numbers from 2 to 100. And so the map F takes something in the power set of X, which would mean some subset of this. So for example, 2, 5, 67. And the map is defined by saying we are going to take this set and it's going to get mapped to the intersection with Y. So really another way to say this is the map F picks out all of the even numbers in the input, right? So you input some set and the output is going to be just the even numbers in that set. So in this case, our output would just be 2. Whereas the function g has the same codomain, which is the power set of x, but it is not mapping back into a similar looking set. It's mapping to the set of integers. So this actually would get mapped to 3 because this has 3 elements in the set. So that's how this function is working. So if I am going to compute g of f of x, so now we're not necessarily going to be able to write out formulas like we did before. So I'm not really expecting that, but what would this function do? Does 2 things, right? And we need to pay attention to the order. So what is going to go in, first of all, is a set. And then first we plug it into F. F is going to tell us what are the even numbers in that set. And then G is going to count how many elements were in that, right? So in the end, if I compose G with F of F, and my input set A is this, right? The first thing that happens is F is going to say, what are the even numbers in this set? And then G is going to count how many elements there are. So in other words, this is counting how many even elements are in A. Okay, which we could write a formula out as it is going to equal the cardinality of the intersection of A and Y. And so the domain, right, would be the inputs into the first function, and the codomain, okay, would now be integers, since what comes out in the end is the codomain of the second function, the outside function. So what would the range of such a function be here? And think about what this function is doing, either symbolically or probably even better, thinking about this. So if I take a set A, which is in the power set of X, what are the possible amount of even elements that could be in set A? So what's the smallest possible value that this function could take?
0.
Yeah, so maybe there's no even numbers in there, and it would be 0. We could have 1 even number. We could have 2 even numbers, etc. And what's the maximum number of even numbers that we might have?
100.
So we've got a total of 100 values in X. And this function is going to count the even elements in there. So what's the most number of even elements that we could have? So 100 is the total number of elements. How many of them could be even?
50.
50, that's right. So our range is now not a continuum of numbers. We're only dealing with integers, but it would be 0, 1, 2, up to 50. So do you think that this map is surjective?
Yes.
It is. So if it is surjective, right, then that would mean every element in the codomain of this map is mapped onto it by some set A. So if we want to determine surjectivity, usually the reason why we indicated the domain and the codomain is we compare them. And if a function is surjective, what should be true about these two sets?
The range is in the codomain.
The range, what should be the relation? Sorry.
It's in, or it's like a subset.
So the range is always going to be a subset of the codomain. If the map is surjective, then what should be true about that relationship?
The range and codomain should equal each other.
That's right. So the reason why we pay attention to, in particular, the codomain and the range is that's going to help us indicate whether this is surjective or not. Since the codomain is Z, that means these are all of the possible values in our, could be output from the function. However, our function only outputs to integers between 0 and 50. So there are tons of values in the codomain, like all the negative numbers, and any number bigger than 50 that are not mapped onto by this function. So this is not surjective since the codomain and the range are not equal to each other. What about injectivity?
No.
Okay, what's a good counter example? So can you give me two different inputs, and by input we mean subsets of X, so that
Either the set of 2 and the set of 2 and 3.
there you go, right? So both of these functions would have an output of 1 because both of those sets have one even number. But those are two different sets. So we have two different sets which are being mapped to the same integer, and that's a problem as far as injectivity is concerned. So this function is not injective and it's not surjective. Okay, and so next, let's think about, well, and any questions, I guess, first of all, about that piece? Okay, so next up would be if we compose things in the other way. So now our codomain would be, excuse me, our domain would be the domain of the inside function g. So my domain here is a power set of X. So what happens now when I try and compose things in this order? So I plug a set, let's kind of do some scratch work over here. Right, so let's say I want to apply this map f of g of 2, 3. So the first thing I would do, right, is calculate g of 2, 3, which gives me 1, right? It would tell me there is one even number. Oh, sorry, that's not right. G of 2, 3 would be 2, because this is just telling us, it's counting how many elements are in the set. And then we would take that output, which is the number 2, and plug it into the map F. Anybody see a problem with that? What would F of 2 be? So Brandon's chatting in, so I'll narrate for Brandon. So Brandon's saying it doesn't seem like a valid entry. Why not? I'll have a chat with Brandon, but feel free. So yeah, we've got a problem here. Does anyone see what the problem is? Yes, thank you, Brandon. And that is that 2 is not a set, right? So 2 is a number as opposed to a set. And so what happens here, the only way that we can compose functions is if the codomain of the first function is equal to the domain of the second function, right? Because I do this function, first I plug it into G, I get the number 2. Okay, well, look, the number 2 is not even in this codomain. So the number 2 is different than the set that contains the number 2. So I'm left with the number. I can't plug numbers into F. So this is actually undefined. So that makes the rest of this problem moot. There's nothing else that we could say. It's not a function, so it is not injective, surjective. It doesn't have any of these properties. So just keep that in mind. Sometimes we can compose things one way, but not compose them another way. Any questions? Okay, so let me, which one did I want to do? Yes, this one over here. So let's take a look at E. Let me get rid of all this. Okay, so now we're going to define function f, which is mapping from the set A, which is real numbers excluding 1, back into the set A, which is the real numbers minus 1. And so now we've got this map f, which is defined by x over x minus 1. And so you can see why we had to exclude 1 from the domain, or else the function wouldn't be defined over its entire domain. So we pop out 1, and we're going to define g the same way. So g of x is also equal to x over x minus 1. So if I want to compose these two functions, let's say I do g of f of x. So this means we are going to take the function f of x and plug it in for each x that we see in G. Okay, and so what I'm doing here is each of the x's, since g of x is defined as the same way, I'm going to replace with whatever, whoops, the input is here. So I'm just plugging in x over x minus 1 for each x in the formula for g. And did anybody get to this part and simplify this?
Yeah.
What is it?
Simplifies the x.
It simplifies to x, that's right. So g of f of x is equal to x. And since f and g are the same, then the order that we compose them is the same. The order that we compose them doesn't matter. So is this function injective?
Yes.
Yep. It's the identity function, right? It's just saying whatever I input into F and then plug into G, I just get the same thing back. So if I plug in two different values into this function, we're going to get two different values out. And there's going to be no problem as far as this thing being surjective as well. We just have a problem that since we can't plug x equals 1 into the function, that means we wouldn't be able to get 1 as an output of the function, but that's fine because our codomain is all reals except for 1. So this maps to everything in our domain. So this is injective, surjective, and thus that makes it bijective. All right, so this kind of brings us to the next point. So I will put up the solutions for these last ones that we didn't get to if you want to think about those. But what's kind of special about this example is that when we compose these two functions, which happen to be the same here, but when we compose these functions in either order, what we see is that we get back the original input that we plugged in. So when two functions have that relation, we call those functions inverses of each other. So one function undoes all of the operations that the previous one just did. So that's kind of why this notion of composition is important, because it helps define what it means to be the inverse of a function. So that just means, again, that when we compose G of F, we get X back. In the example that we saw that that X over, I think it was X minus 1, those functions are inverses. So actually that is a function whose inverse is the same function as itself. Okay, that's very special, this case here, where the function is its own inverse. Usually, almost always, they're different, right? So here's a very basic example. If f of x is 2 of x, its inverse would do the opposite operation, which is divide by 2. And then we can check that when we compose those two functions, first divide by 2 and then multiply by 2, we get x back, and vice versa. Okay, so inverse functions are really nice. They help us solve equations. They have really nice properties overall. And so what is really nice about these properties of injectivity and surjectivity is that if a function satisfies both of those properties, so if a function is bijective, then it's invertible, and vice versa. So the only functions that have inverses are bijective functions, and all bijective functions have an inverse. So it goes in both directions. And so for the proof, we can just kind of walk through this together to see how this goes. But it's double implication here. So it's an if and only if, a biconditional statement. So that means we've got two directions that we would need to prove. And so for the forward direction, we're going to assume that this function is invertible. And what we need to show is that therefore that function is a bijection. And so we can start with a function f, and we're going to assume that it has an inverse. We'll call it g. And this is okay to claim because, again, this is our hypothesis when we're going in the forward direction. So then that would mean that when I compose f and g, right, they undo each other. And this is basically using the definition of what an inverse function is. So that gives us surjectivity. For any y in the set B, which is the codomain, we can see that when we compose f and g, it's possible to get y as an output. So what we can see is that f has y as an output for all y's in B. So it is surjective. So in order to prove surjective, that's exactly what you need to prove, that for any element in the codomain, there is some element that gets mapped to it. And in this case, the element that gets mapped to it is g of y. Any questions? Okay, then the next part would be to prove that this is injective, and then that would prove the forward direction, right? That it's both injective and surjective. So we did surjective up top. In order to prove that this is injective, then we can either do this contrapositively or directly or whatever, but the gist is if two inputs are different from each other, then it shouldn't be the case that they give me the same output. So here, this proof is being done by contradiction, or contrapositive, I should say. So we're going to assume, well, this is being done by contradiction. So let's suppose that they have the same output. We'll call it y. Then we can show that that would imply that its inverse, g is the inverse, undoes this operation. So if I take g of y, I get x1. I take g of y, I also get x2. And since g is a function, right, it's not possible for y to have two different outputs. So that's a problem there. So y should only go to one output. So it has to be the case that x1 is equal to x2. And that's a contradiction from what we assume that they were not the same element. And so that gives us the injective side of that. That would be the forward direction. But any questions? And so then for the reverse direction, we start by assuming that the function is bijective. And we want to show that it therefore is has an inverse, right, is invertible. So we start with saying f is bijective, so that means it's surjective. So every element in its codomain, we'll call it y, has some element from A that is mapped to it. That's what the definition of surjective would allow us. So that means for any y, there does exist some x, so f of x is equal to y. And then furthermore, since this is injective, there's only one element which is mapped to y, right? So for any y in B, there is exactly one x in A that is mapped to that y. So that's what the injective and the surjectiveness of f allows us to say. First of all, there does exist an x. Secondly, there is only one of them. There can't be two of them. And once we get that, we have now a nice way of defining the inverse function. So we're going to define the inverse. Well, we're going to define this function g, and then we'll show that g is the inverse by saying, okay, now we need to define a map that goes the other way from B into A. And so we're going to take an element y, and we need to know where to send it. Where is it going to get mapped to in set A? We're just going to define, by this map G, we're going to define G of y is equal to x. So in other words, G is telling us what was the element from A that was mapped to y. And what's important is we know that for every y, it has an x and that it only has one. That makes G a function. And then from there, it's just show that when we compose these two functions in either order, G of f, sorry, G of f gives me x. And when we compose it in the other way, we get y. So this, by definition, would tell us that G is the inverse of f. So f is invertible. So big takeaway here is these two terms can really be used interchangeably. If it's bijective, it's invertible. If the function is invertible, it's bijective. Questions? So kind of the upshot for that is when you're dealing with questions like this, determine whether each of these functions is invertible. You have kind of two techniques. So if it is, we can either do a non-constructive proof. So if your question is prove that f is invertible, if you prove that f is bijective, that would be a good enough proof. So in other words, proving that it's surjective and injective would be enough to prove that it's invertible. So in some sense, we've been doing these proofs already because we've been proving bijectiveness of functions. If it's not, or I should say, now we have a second possibility, which is even easier. If we can give a formula for f inverse, then we're done, right? That would be a constructive proof. We proved that inverse exists by constructing it. So you have two possibilities there. I will say, like, when you're dealing with functions from R to R, where we have some intuition already, we can go ahead and just construct these inverses if we like. So if I'm looking at this function in A, right, we can see that this does not pass the horizontal line test. So if I want to prove that this is not invertible, since f is not injective, then it is not going to be invertible. If we tweak that function a little bit, oh, that's right below. So if I tweak it to this, and I map it into R, then this function in part B okay, but it's not surjective since -1, right, is an element in the codomain, but it's not in the range. So if I go from 0 to R, I get something which is now injective. Each element gets mapped to a unique thing, but not everything in the codomain has a pre-image. So this one would also not be not invertible. Okay, whereas if I restrict both the domain and the codomain to be non-negative numbers, then this would be invertible, and my proof for this would be square root of x, right? And now when I restrict this codomain, suddenly these inputs are okay over here. So if I wanted to prove that the one that I boxed in blue is invertible, well, that would be my proof. See, here's the inverse. And if you wanted to verify that, then you would just want to check that when you compose these functions in both orders, you need to check both order, we get x back. So that would be a proof for invertibility would be, here's my function, and now I've just proven that this function is the inverse. Okay, so we are out of time, so I'll stop here. Next time, we're gonna move on into chapter 14. So happy to go over these. I might leave these problems for you to consider at home, and I'll write up the solutions. You know, these are things that you probably have seen before. Is this invertible? Is that invertible? So on. And so the reading assignment for next class is going to be about cardinality of sets. And I think we'll do some really interesting things and see that not all infinities are created equal, and some infinities are bigger than other infinities, and some weird counterintuitive or maybe intuitive things, some interesting things about sets. And that will be it. So we're going to end the semester talking about chapter 14. We're going to skip over chapter 13 in the middle. Okay, well, thanks everybody. Have a nice afternoon. Reading assignment should be open shortly, and your homework assignment would be to kind of go through this worksheet, finish up this, and see if you have any questions. And there's a longer homework, it's not that long, but your last homework assignment is also posted, and that is due after Thanksgiving. Some of it we haven't gotten to yet, we'll get to next time, but some of it we certainly have, so you can get started on that if you like. Okay, have a nice afternoon, and I will see you guys on Wednesday.